Today we're talking about radian and degree measure, one day of several that we're going to split our time up on. We're focusing specifically on drawing these angles in what we call standard position, how do we identify what quadrant the terminal side of the angle shows up in, and how to find coterminal angles. So that's our topics for today. Okay, so here is our angle. So here is a general angle. The concept is if you take a ray, so it has one endpoint and it continues on one side, and you sort of copy and paste it so that the two rays are joined at their endpoints. Well, we call that the vertex of the angle. So we have an initial side and a terminal side, but we want to place it in such a way that the vertex is at the origin and the initial side is on the positive x-axis. So it would look like this. So when we draw our angles, we are either rotating in the positive direction, which is this counterclockwise direction, or as you'll see in a moment, it will rotate in a clockwise direction, which will be the negative direction. We can use a variety of symbols to represent these angles. We can use T, which stands for theta, or the Greek letter theta, or alpha or beta. Those are the most common symbols that you will see representing a variable for the size of the angle. When we're talking about finding coterminal angles, we can do that in both degrees and radians, and we'll come back to these formulas in a moment. But the reason why we're adding 360 and also subtracting 360 is because we can rotate in either direction. So there it is, your positive angle moves in that counterclockwise direction, and your negative angle moves in that clockwise direction. So let's take an angle here and just kind of diagram out what a coterminal angle looks like. So let's imagine for a moment, I didn't draw that quite to scale, but let's imagine that's 120 degrees. So if we were to start at the same initial side and finish at the same terminal side but rotate clockwise, that would also be a coterminal angle. This would be a different sized angle. It's 240, but it's not 240, it's a negative 240 because of the direction in which we're rotating. Another way to identify a coterminal angle is we could use that 120 degree angle, but we're just going to keep rotating past it and continue around. So we would spiral around. So we would start here, there's 120 degrees, we keep rotating around until we come across it the second time. So we're still terminating in the same spot. That means we've added 360 degrees on top of the 120. So that would also be a 480 degree angle. So you could keep adding 360 as you keep going around and around and around, or you could keep subtracting 360 as you keep going in the clockwise direction. So here's a brief introduction for radian measurements. Radians are like learning a new language, I feel, because we're very comfortable with degrees, but we don't use radians all the time, and, well, they're not very intuitive sometimes, because oftentimes we measure radians in terms of fractions of a pi. So we have to develop our skills with fractions while we're also figuring out how to measure these things. So the way that this is defined is we're taking the radius of a given circle, we're taking that length, we're copying it, and then we're pasting it and wrapping it around the edge. So if we were to take the length of that radius in the diagram, and here's the radius, instead of a straight radius, we're wrapping its length around the circumference. However far that is, where that radius terminates, we're going to draw the second side of the angle to that little wedge right there. That is an angle of what we call 1 radian. And you can kind of see that in more detail in this diagram down here in the bottom right corner. So if we wrapped 1 radius around the circumference, that's an angle of 1 radian. If we had 2 radiuses wrapped around the circumference, that's an angle of size 2 radians. 3 radiuses wrapped around the circumference would create an angle of almost 180 degrees, but not quite. That's 3 radians. We're just short of that halfway mark, and so as you might remember, pi is a radian measurement. That is about 3.14. So you can see that's 3.14 radians as opposed to the 3 radians that you see marked there with 3 radius lengths around. 4, 5, 6 radians, and then we're back to where we started with, and that's 2 pi radians all the way around, so about 6.28. Now, what happens if we want a distance around the circle that's not exactly 1 radian? Like, what if we only want to go this far, or we want to go somewhere between 1 and 2 radians? How do we calculate that length? We have a formula for that. We'll see that on the next page. And so that's going to be represented here in this diagram that we're going to draw right now. There's our circle, there's our center, there's our radius. All right, so let's say we want a distance around the circle that's not just 1 radian or 2 radians. Let's say it's some random distance, so let's call that. Here, let me finish off the angle there. That's the angle of theta. We need another symbol here, and forget my scribble. We want to use the letter S. That stands for the distance around a circle, but not all the way around. All the way around would be the circumference. We're going some of the way around, so we call this the arc length. And we can use that arc length and the radius to help us find that angle of rotation, which we're actually doing in the next lesson. It doesn't really show up here, but we're introducing it here just because we're talking about wrapping the radius around the edge of the circle, and what if it's some other size. So we'll come back to that formula later. That theta is your central angle, and then of course the r is the radius. Of course, you're more familiar with degrees, and so here is the 360 degrees divided down into smaller portions. We'll be coming back to this later when we talk about our unit circle. And so you can see if it's 360 all the way around, then the halfway point would be half of 360. That's why it's 180. And 1/4 of a revolution would be 1/4 of 360 degrees, so that's 90. So we can keep setting that to smaller and smaller increments. All right, so that's the introduction. Let's go to our examples. We are looking at these specific skills. We want to draw the angle. We're really doing that in these top 2 rows. But in the top row, in addition to drawing the angle, we want to determine the quadrant in which the angle lies. What we really mean is determine the quadrant in which the terminal side of the angle lies. All right? What we want to do is build our skill with radian measure. So when we see a problem with radians, we're going to do the work in radians. We're going to think in radians so we can get better at radians. We're not going to convert that into degrees to make it easier on ourselves. If the problem is already in degrees, that's fine. We'll think in degrees and we'll put our answer in degrees. So that's our sort of rule of thumb. The problem is in radians, do the work in radians and give the answer in radians without converting it. Unless the problem actually asks you to convert it, okay? So let's see, where is 7/4 pi? We're going to draw that angle and then we'll determine where the terminal side of that angle lands. So the first thing we do is we look just to see which way we're rotating. Is my angle positive or negative? It is positive. So that means we're rotating in this direction, counterclockwise. So that's what the CCW is there for. Then we're going to identify some landmarks. The halfway point is exactly pi, radians, which we know is about 3.14. But we have to think of this in terms of fractions of a pi. So my major landmark here is 1 pi with a denominator of 1. But our problem has a denominator of 4. So we're going to multiply this by 4/4 to create a common denominator. What that means is if we rotate around, that is a rotation of 4/4 pi. We want 7/4 pi. So what we're doing is we are subdividing the top half into fourths of a pi. So there's 1, 2, 3, 4. If we were to take the time to label it, this would be 1/4 pi, and then 2/4 pi, which reduces to pi over 2, 3/4 pi, and of course there's 4/4 pi on the left. So now we have to subdivide the bottom half into fourths as well. So here's 5/4 pi, here's 6/4 pi, which reduces to 3/2, and then here's 7/4 pi. We found it. So the initial side is on the x-axis, the terminal side is right there. Draw the spiral so we can see where and the direction that we're rotating. And the answer is quadrant 4. So remember, they are numbered off in that counterclockwise direction as well. So yeah, our terminal side ends up in quadrant 4. So there's the answer. So let's take a look at another example. Number 2. This time we have a negative angle, so that means we're going to rotate in the clockwise direction, this direction like that. So, again, we have the same denominator of 4. My major landmark is at the halfway point, which is a pi, but it's a negative pi because we're rotating in that direction with a denominator of 1, so we need to multiply that by 4/4. So this is negative 4/4 pi. So as we take the bottom half of this diagram, we're going to divide this into 4 equal parts. Each of them are a -4 of a pi. So this is -1/4 pi there in quadrant 4. Then -2/4 pi, which reduces to -pi/2. Then -3/4 pi there in quadrant 3. There's -4/4 pi on the far left-hand side. And then we divide the top half also into 4 equal parts. So here's -5/4 pi. Up at the top, -6/4 pi. That reduces to -3/2 pi. Quadrant 1, that's -7/4 pi. And we get back to where we started from, and that's -8/4 pi. Obviously, we haven't gotten to 11 yet, so let's keep on counting. That was -8/4 pi on the right. Next is -9/4 pi. The bottom is -10/4 pi, and here on the left we have -11/4 pi. So I'm going to label that as well with what room I have, -11/4 pi. There it is. That's where the terminal side goes. Now we spiraled around, so you have to draw that loop like so to kind of indicate that you went around more than once. We ended up in quadrant 3. So again, even though we were rotating in a clockwise direction, the labeling of the quadrants is still consistent with that counterclockwise direction of labeling, so that's why we're still in quadrant 3. Here is an angle measure without the pi symbol. Where is 4.2? Now think about this. Is that degrees or radians? It doesn't have the degree symbol, like you see in example 4. So it's not degrees. That means it is still in radians. Up to this point, we just looked at how to find fractions of a pi around the circle, but what if we don't have pi instead? So now we have to think about where would we normally find the radian measure of just integers, 1, 2, 3, 4, right? So if you take the radius, and you spin it around, 1 radian is about here. Remember, you can go back to the previous page and take a look at what we saw in the diagram right here. That's 1 radian, that's 2 radians, that's 3 radians. Again, you can still use pi as your landmark because that's about 3.14. So we would know our angle of 4.2 radians definitely has to be beyond the halfway point, and so you can see it's about right there. So 4.2 radians is what we want. So here's about 1 radian, here's about 2 radians, here's 3 radians, and approximately there's 4, so we'll call this 4.2. There's the terminal side of the angle. There's the direction of rotation because it's a positive angle, so we're going in that counterclockwise direction. And we end up in quadrant 3. All right, you may have some relief now that we go to degrees. Where is 200? No, where is -240 degrees? That negative sign means we're rotating in that clockwise direction. So we rotate down to the bottom, that's -90 degrees at the bottom. On the far left, that's -180. And at the top, that's -270. And back where we started from is -360. So -240 will be right about there. And you could label that as well. We are in quadrant 2. Quadrant 1, quadrant 2. We're going to continue that skill in the next row as we're going to draw some more of these where we have some odd-looking denominators in our fractions here. It just says sketch the angle in standard position. It doesn't actually tell us to identify the quadrant, but we could if we had to. So let's take a look at number 4. Where's 11/6 of a pi? If you're familiar with the unit circle, you'll know where that is, but let's say we don't know where that is. How would we go about that? Same method as before. First, identify which way you're rotating. This is positive, so counterclockwise is what we want. Then, we want to identify our landmark. So halfway around is pi with a denominator of 1, but we want to match the denominator 6, so multiply by 6/6. So think of this like 6/6 of a pi. So we're going to divide the top half into 6 equal parts. 1, 2, 3, 4, 5, 6. So 1/6 pi, 2/6 pi, 3/6 pi, 4/6 pi, and so on. Then divide the bottom half into 6 equal parts. 1, 2, 3, 4, 5, 6. And let's find where that 11/6 of a pi mark was. So 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. I think I got too many markings in here. Oops. Well, that doesn't help any. 7/6 pi, 8/6 pi, 9/6 pi, 10/6 pi. There's your 11/6 pi. I think I put 7 marks on the top half instead of 6. That's my fault. There it is. We're in quadrant 4. All right, number 5, we're rotating in the clockwise direction with a negative sized angle. So halfway around is my landmark of negative pi with a denominator of 1. We're matching that denominator of 4, so I want to divide it into 4 equal parts. So there's 1, 2, 3, and there's the 4th mark. So negative 3/4 pi is here in quadrant 3. What if we have a really odd denominator like 13? All right. First, it's a positive angle, so we're rotating counterclockwise. Use your halfway point as a landmark. Again, that's a pi with a denominator of 1. We want to create 13/13 pi to match our denominator of 8/13 pi. So that means we're taking the top half and dividing it into 13 equal parts. Well, this is another major landmark at the top, right? That would be the halfway point between 0 and 13/13 pi. So it's half of 13, 6.5, okay? So that means we need 6 tick marks on the right and about 6 on the left. So 1/13 pi, 2/13 pi, 3, 4, 5, 6/13 pi. There's 7/13 pi, 8, 9, 10, 11, 12, and there's your 13/13 pi. So there's my 7th, there's my 8th. That's what we want. So obviously we're kind of approximating where that angle lies. We're doing our best to equally divide those angles of rotation, and that's what we're looking at there. Let's finish up now with some examples on coterminal angles. We're going to find 2 of them. With this restriction, we want to find one that's positive and one that's negative. So let me take you back to the formulas, the little aids that we had on the previous page. If we have an angle in degrees, we'll take that angle, we'll add 360, and we'll subtract 360. But if we're in radians, we'll add 2 pi and we'll subtract 2 pi. Let's see what that looks like. So in number 7, we're starting off with 11/6 of a pi. So take your given angle. We want to add a revolution of 2 pi. That is a denominator of 1, but we have to have a common denominator. So we're multiplying top and bottom by 6. So this means we have 11/6 pi plus 12/6 pi, and that gives us a total of 23/6 pi. That's essentially going around one more time. That'll terminate the same spot that 11/6 pi does. To find the other, let's take again the given angle of 11/6 pi, and this time we subtract 2 pi. Again, you need a common denominator, so multiply by 6/6. So now we have 11/6 pi minus 12/6 pi, and that's a negative 1/6 pi. We can format it this way, negative pi over 6. We got one positive, one negative. We met the conditions of the problem, so we're good there. Here's number 8. This time we're starting off with a negative angle of negative 13/4 pi. So take the given angle, and I'm going to add 2 pi. We have to match that denominator, so we're multiplying by 4/4. So we have negative 13/4 pi plus 8/4 pi, and that gives us a result of negative 5/4 pi, which is still negative. That's interesting. Notice we added something, but it was still a negative result. What that means is this initial angle was a very, very negative angle, right? So I don't want to subtract 2 pi because that would turn it negative again. What we have to do is take that result and keep adding 2 pi until we finally end up with a positive coterminal angle. So once again, we need to match that common denominator. So negative 5/4 pi plus 8/4 pi will give us a positive 3/4 pi. There we are. So we have one negative, we have one positive, we met the condition there. So we're good. You can probably handle the one with degrees just fine, but here it is just in case. If you have an angle of 155 degrees, let's give it a rotation of 360. And a little calculator work here gives me a result of 515. If we subtract 360, we get a result of negative 205. So those are the coterminal angles. We found one positive and one negative.